All right, here we are, the method you've all been waiting for, the midpoint rectangular approximation method. So still we're dealing with y equals x squared plus 1 on the interval 0 to 4, and we're going to start with 4 subintervals. All right. So again, start off by drawing our picture. So here's our graph. One, two, three, 4, and there's 0. So what happens now with these guys, all right, is that we're still dealing with our rectangles. It's just that now we're going to use the midpoint of 0 and 1 for our height. Now we're going to go here, we're going to go up and over like that. Over here for 3, we're going to go up, over, and up again. And then 4, it's going to be really pronounced, like that. So if you notice now what's happening with this graph is that since we're going with the midpoint, all right, I'll point to this one over here. Since we're going with the midpoint of the interval between 3 and 4, we have a little bit that's on the outside and a little bit that's on the inside. So if you think about it, this little part here that's an overestimate can fill in the part that's over here that's an underestimate. So by using the midpoints, the idea is that the part that you have on the outside and the part that you have on the inside will end up just washing out in the end. So all of these still have a width of 1. So it's going to be 1 times, I'm going to factor the 1 out. All right, and we're going to look at f of 0.5 plus f of 1.5 plus f of 2.5 plus f of 3.5, because we're going with the halves. All right, each of these is f of 1/2, f of 1 1/2, f of 2 1/2, f of 3 1/2. Those are all of our individual heights. When you work this out, you get an area of 25, which is really only off by 1/3, which is pretty impressive considering how much we're going over and how much we're going under, and that we're only using 4 subintervals. In an effort to be consistent, we're going to do the same problem again, only now we're going to look at 8 subintervals. Eight subintervals gets kind of crazy. 0, 1, 2, 3, 4. So for each of these subintervals, right? So we had 1, 2, 3, 4, 5, 6, 7, 8. Good. So now I'll start here. That's our first guy. That's our second, third, fourth, fifth, sixth, seventh, and eighth. Down here towards the bottom, because the interval is so small and the rate of change of the graph is so slight, it basically looks like you're hugging the curve. It doesn't become more pronounced until you get all the way up there. Okay. So each of these have a base of 1/2. Okay. Each of these has a base of 1/2, so you end up with f of 1/4, f of 3/4, f of 1 1/4, f of 1 3/4, f of 2 1/4, f of 2 3/4, f of 3 1/4, plus f of 3 3/4. Now, some of you might be at home wondering, where the heck is he getting the 1/4, 2/4, 3/4? Remember, this is 1/2 right here. So the midpoint between 0 and 1/2 is 1/4. Between 1/2 and 1 is 3/4. And since they're all separated by 1/2, you just follow the pattern: 1/4, 3/4, 1 1/4, 1 3/4, 2 1/4, 2 3/4, 3 1/4, 3 4/4, all the way through. Each of these get plugged into f of x. You end up with an area equaling 25.25. Remember, our actual area is 25.3333. Repeating, you have to admit, that's looking pretty darn good. Pretty darn good. Okay. So what I'm going to try to do right now is sum up the 3 types of approximation methods. Okay. You have, in conclusion, you have your left rectangular approximation method. Okay. This is b minus a over n times f of x sub 0, f of x sub 1, f of x sub 2, plus blah blah blah, plus f of x sub n minus 1. Okay. So what we're doing here is that we're finding the area underneath the curve on a closed interval from a to b. So if you're given f of x on the interval ab with n subintervals, these are the shortcut formulas to make life go a little bit easier for you. So if you have f of x on an interval from ab with n subintervals, the left rectangular approximation is your upper bound minus your lower bound divided by the number of subintervals times your first point plus your second plus your third, all the way out to your second to last point. We're going out to n minus 1. Okay. The right rectangular approximation method, still dealing with this stuff. You still have b minus a over n, only now it's going to be f of x sub 1, f of x sub 2, f of x sub 3, plus f of x sub n. So here in the left rectangular approximation, in the left you include the first point, but you skip the last one. With the right rectangular approximation, you skip the first one, start with the second, but then end with the last. The midpoint approximation is still b minus a over n, only now you're going to do f of m sub 1, f of m sub 2, f of m sub 3, going out to f sub m of n, where m sub n is the midpoint of each subinterval. So the midpoint approximation really isn't my favorite, but you know, it works when it needs to work. All right. So these are the rectangular approximations, and it's based upon these rectangular approximations that Riemann sums, which is the next video, is based upon. So we had to do this so that the next thing I talk about actually has makes some sense. All right, otherwise we would have just been, wouldn't have made anything. So, all right, thank you.